All right, so our second to last section in this unit. I feel like the chair is lower today, so hello everybody. Second to last section in this unit is going to revisit the idea of the counting principle. We talked about the counting principle when we dealt with tree diagrams, so it's just said again, but we're going to go a little bit deeper into some implications of the counting principle. So remember, the counting principle says if a first experiment can be done in M ways, or it has M distinct outcomes, and a second experiment can be done in N distinct outcomes, if the two experiments are done together, it has N times N outcomes. And the example we did last time, okay, this was at the top of the page right after the counting principle, was this. It was how many outcomes if I flip a coin and then roll a die. You don't have to write this down. I mean, you're welcome to write this down. This was the example. It's at the top of the section 11.4 sheet. And we said, okay, well, this was just a little example of the counting principle. How many ways can you flip a coin? How many outcomes are there when you do that? There are 2. And then times, how many outcomes are there when you roll a die? 6. And so when you do those two things together, then there are 2 times 6 or 12 outcomes. And where we took it then, where we took the counting principle last time, was we did tree diagrams and we were able to list out all the outcomes. So now we're going to take the counting principle in a little bit of a different direction today. So for instance, example 1, you need to make a 4-digit passcode for your phone. Okay, so phones have increased the number of digits, and you're going to see why in just a minute. So you need to make a 4-digit passcode for your phone. How many different passcodes are possible? Okay, so why is that done? You know, why are there 4 digits as opposed to 3 or 6 or 9? What's the difference? Okay, well, let's do this then. If I'm guessing the passcode, okay, so if you grab somebody's phone and they got a 4-digit code, how many options are there for the first digit? 10, 0 through 9, that's 10 digits. Okay, so 10. How many options are there for the second digit? 10. I'm going to ask it 2 more times. How many options for the third? Yes, and finally for the last, 10. Okay, so for each of the 4 digits, this is digit 1. So whatever your passcode on your phone is, if it had 4 digits, then you had 10 options for each of the 4. And when you do 10 times 10 times 10 times 10, you get 10,000. Okay. So that means if somebody grabs your phone, there are 10,000 different options. So they have a 1 in 10,000 chance of guessing your passcode on the first time. Okay, so that's kind of the reason for the passcode, keeps us safe. But you know, people are clever and computers are helpful. So what I want you to do is example 2. So a couple of years ago, Apple mandatorily increased the number of digits to 6. You can do more, but you have to do 6. Why? What's the implication? So do example 2, please. Okay, so here goes. This time we have 6 numbers on our passcode. So I'm not going to bore you by asking you the same question, but when you make that code, when you get your brand new phone and you peel off the nice plastic front of it, okay, you have 10 options for the first digit and 10 options for the second, 10 for the third, 10 for the fourth, 10 for the fifth, 10 for the sixth. And so that means that you have 10 to the 10 times 10 times 10 times 10. That is 1,000,000 different options. So you can see when Apple and Android, when they made you pick 6 digits instead of 4, it's making it harder for somebody to randomly guess what your passcode is. So my daughter, who's very paranoid, she has a 12-digit passcode. So I can't even remember strings of numbers that long. So good for her. Anyway, she wants to be real sure no one's going to randomly guess. So continuing the counting principle, so we saw in those 2 examples, we could pick any, there was no constraints, but what happens if there are constraints on something? So for instance, example 3 says, You need to make a password consisting of 2 lowercase letters followed by 4 digits. So we're just kind of keeping this structured a little bit just to limit the number of options. So you have to have 2 digits, 2 lowercase letters followed by 4 digits. So I'm going to help you with the A part, and then you're going to give a good try to the B and the C part. So how many possibilities are there if repetition is permitted? Okay, repetition's permitted. So if I have to have 2 lowercase letters and then 4 digits. So for my first lowercase letter then, how many options are there? Yes, there you go. Your elementary school education coming back to you. Excellent. How many options are there for the second lowercase digit? Yes. I'm just going to call a timeout because we know a lot of websites that case matters. In fact, almost all websites, case matters. So if I said instead of lowercase, if I said 2 letters of any case, how many possibilities would there be? 26 times 2, 52. Yes, that's exactly right. 26 times 2 is 52, so there'd be 52 options. Yes, so by saying case matters, and you've got to put, like if you go to a website that says you have to have at least 1 capital letter, you got to have 1 exclamation point or whatever, that's what they're doing is they are increasing the number of options so to make it even harder for somebody to guess, or make it harder because really it's not a matter of somebody guessing, it's a matter of a computer program, and it takes the computer program even longer in order to figure it out. Okay, anyway, sorry, all that's just a little diatribe. 4 digits. So you already told me there's 10 digits. So 1, digit 2, digit 3, digit 4. And so when I do 26 times 26, and then times those 4 tens, which turned out to be 10,000, that is 6,760,000 different options, which is a lot, and it sounds like a lot, but unfortunately, computers can think so fast that would not take a computer a long time. By the way, just as an aside, when you do make passwords, it's not necessarily being clever and putting lots of symbols in it. The thing that makes a good password is length. So even if you can think up like a simple sentence that you can remember, the longer you make the password, the more secure it is, because it's going to take, so like for instance, I have a short Bible verse that I use that I remember. So I type that in, and so then it's longer, and so computers can't come in. So anyway, just as an aside about making computer passwords for websites and things like that. All right, so here's what I would like you to do. The B problem. So I'm giving a constraint now. It's the same 2 lowercase letters and 4 digits, but this time repetition of the letters is not permitted. So you can't repeat. So give it a try, see how you do. Okay, so repetition is not permitted. So how many choices are there for the first letter? Still 26. Okay, but I can't repeat. So whatever letter I've just picked, I can't use again. So that means how many options do I have for the second one? Perfect. Great job, everybody. Appreciate that. There are 10 options for the first digit. So now that I've used that digit, how many options are left for the next one? And then for the next one? And then for the last one. Perfect. Well done. I appreciate that. So now I multiply those, and you can check my work because we saw that my large fingers messed up last time we were together. That is 3,276,000 different options. Okay, so for the C problem, I added even more constraints in. So the C one, the first letter must be a vowel. Okay, and we're only considering well, I guess we'll go A, E, I, O, U, and then sometimes Y. We'll use the sometimes Y, so those are the vowels. Some people like to think W is a vowel. I do not know what world that is, but that's okay. So the first letter must be a vowel, and the first digit cannot be 0, and repetition is not permitted. So a bunch of constraints just to keep you fresh today. No repetition of anything is not permitted. Okay, so I told you in the constraints, the first letter has to be a vowel. So that means how many options do I have? Yep, A, E, I, O, U, sometimes Y. I declared it at the beginning, so 6. So whatever vowel I use right there, though, I can't reuse. So how many options are there for the second letter? Okay, now I said the first letter must be a vowel. Did I say the second one had to be a vowel? No. So how many options are there for the second letter? There's still 25 because there's 26 letters total, but I used one of the vowels, and so now there's 25. Don't worry. I mean, if you missed it, don't worry. That's why we do these problems. So just learn. You're doing great. Okay, and then 0 the first digit cannot be 0. So how many options are there for my first digit then? 9. And now I just said the first digit can't be 0. I didn't say you couldn't use 0 at all. So now for the second digit, how many options do I have? I still have 9 because we throw 0 back into the mix, but I have one number that I can't use. So I still have 9, and then 8, and then 7. Everything goes back to normal. So I have 6 times 25 times 9 times 9 times 8 times 7, and you get 680,400. We doing okay? I know that was a hard one. It's difficult. So like Florida license plates are done like that. The standard way, not if you have a vanity plate or anything, but the standard way to do a license plate in Florida is there's 4 letters and then two numbers. And so you could now determine, I don't know if there's any constraints. I think you can use all the letters, all the numbers. I don't know that much about Florida license plates. So then you can figure out how many possible license plates can be made just with those standard things. Okay, example 4, I want you to give this one a try. You've got 6 family members' pictures in frames and you want to hang them on the wall. Okay, so you want to hang the pictures on the wall. How many different ways can you arrange the 6 pictures on the wall? Okay, so how many options are there for the first picture? 6, great. And so you hang Grandma Marie up on the wall, and now how many options are left for the second picture? Now I just have 5, because I've taken one of the pictures, I've hung it on the wall, so it's no longer in use. So I have 5. Okay, so I put Grandma Anna. Those are my grandmothers. Rest in peace. All right, and so now I've hung those 2 up there. How many options are there for the third picture? Okay, 4. And then for the 4th one, there would be 3 options, and then 2 options. And finally, you're left with the last picture, so you only have 1 option. Does that make sense to everybody? We're using the tangible real world example that I'm hanging pictures, so I can't hang a picture up more than once. Okay, so that's why the number of options goes down. So 6 times 5 times 4 times 3 times 2 times 1 turns out to be there are 720 different arrangements of those pictures on the wall. Now, what we have here is a situation where order matters, right? Whoever I hang up first, that is different. So if I put Grandma Marie up first, that's different than if I put my wife Missy up first. That's going to be a different arrangement of objects. Okay, so what we have here, and this is where we're driving the bus today for the counting principle. Okay, last time we used the counting principle and we talked about tree diagrams. This time we're using the counting principle and we've come up with this idea of an ordered arrangement. And that in probability and statistics is called a permutation. A permutation is an ordered arrangement of a given set of objects. So here's the thing, when you do your homework this weekend, on this section, this is the thing I need you to focus on. When you're doing these problems, I need you to focus on why does order matter? Because when we come back next time and we do the last section, we're going to talk about an arrangement of objects where order doesn't matter. Okay, where it doesn't matter which one comes first or second, it's the group that matters. Okay, so when you take the test, I'm not going to tell you whether it's a permutation or the other thing that we'll talk about next time. Okay, so when you're doing your homework, focus on the idea of why does order matter in this situation. Okay, so in the example we just did, order matters because each of the pictures is different. It's a different family member. Okay, so that whoever's first and second is going to be different. So the way we calculate the number of permutations of n distinct objects, so n is just a number. So like in example 4, I had 6 objects. In the next example you do, you're going to have 7 objects. So the number of arrangements is given by this. It's called n, I'm going to put an exclamation point. I don't know if you've ever seen that. I'm not assuming that you have. What that is called in math, when you have that exclamation point, it's called a factorial. It doesn't mean to say n really loud, like n, yes. And what the factorial means is you keep multiplying every whole number from where you start till you get to 1. So for instance, if I asked you to calculate 10 factorial, what 10 factorial means is you're going to start with the number 10, and then you're going to go down, and you're going to say, okay, times 9, times 8, times 7, times 6, times 5, 4, 3, 2, 1, blast off. There we go. That's what factorial is telling you. You start with whatever number is there, and then you count by ones, and you keep multiplying all the way till you get to 1. Now, I don't expect you to do all that multiplying if you don't have the proper calculator, you're going to have to. But most calculators, if you have any scientific calculator, this is supposed to be locked. If you have a scientific calculator, you'll have the ability to do a factorial. So on this calculator that I am using, let's see, where is the factorial button? Hard for me to see because I'm not wearing my glasses. It's somewhere. There's an exclamation point on here. Oh, there it is. It's right above the number 3. So this calculator has an exclamation point. So as you see exclamation point, if you have a different type of TI or if you have a Casio calculator, or actually I think the Casio calculators have the button. If you have a different TI, you'll have a button that says PRB on it, and that'll give you a probability menu. When we're doing the next problem, if you don't know how to use your calculator to calculate a factorial, just wave your hand. It'll take 2 seconds to find the button. So what I'm going to do on this calculator is I'm going to hit the number 10, and then I'm going to hit the second button so that I can use the factorial. And so there it is. That's 10 times 9 times 8 times 7, and it turns out to be 3,628,800. 800. Okay, so 10 factorial is 3,628,800. So above, for example 4, we didn't know about factorials. We just listed all the options. Now I can go back to my calculator and say, okay, what's 6 factorial? Does that agree with what I got? So 6. Then I'm going to hit the second button. I'm going to hit the exclamation point. Yes, 720. So that's just a very quick way to be able to do that calculation. So here's what I would like you to do. Example 5. You have 7 books. You're going to place them on the shelf. You want to do some decorating. How many ways can you put those 7 books on the shelf? And if you need me to help you with the calculator, let me know. Okay, so for example 5, it says we have 7 books. We're arranging them on the shelf. The reason order matters here is because I'm assuming they're different books. And so depending on what one I put first, it's going to create a different arrangement. So we could do this the regular way if you wanted. You could say, okay, for the first book, I have 7 options. For the second book, there are 6. For the third book, there are 5, and then 4, and then 3. These numbers are not too bad. My pen is not wanting to write for some reason. Or you could say, okay, we've got an ordered arrangement of objects, and so that is just equal to 7 factorial. Either way you calculate it, okay, I would prefer you get used to using the exclamation point. That's going to help you in just a minute when we go a little deeper into this. But I'm going to do 7, and then I'm going to hit my factorial button, and that's 5,040. So there are 5,040 different ways you can arrange 7 books on the shelf. Do example 6. So again, how many letters do I have here that I'm trying to arrange? I have 5 letters that I'm trying to arrange. Fantastic. So that means there's 5 options for the first letter, 4 for the second, 3 for the third. And so what that is 5 factorial. That's the number of arrangements of those 5 letters when I take into account order matters. And so then 5 factorial is going, what did you get for 5 factorial? 120? Perfect. So there's 120 different ways. If you are using all 5, so I'm going to circle here all 5 because here is the last thing that is new for our section. Okay, we've talked about the counting principle and using it to figure out arrangements. And then we said, okay, if I have a given number of objects and I'm using all of them, that became what's called a permutation. So now for example 7, I'm going to help you with this one. Example 7 says, for the previous example, how many arrangements are possible if just 3 letters are selected? So instead of using all 5, I'm just using 3. Well, here's what you would say. I think you could have done this problem even before we talked about permutations, but I want to link this to our formula. So how many options are there for the first letter? 5, and then how many options for the second? 4, and then for the third, there are 3. And so that's going to end up being 60. And so the question is, okay, is there some way that I can alter my permutation formula? Because the permutation formula is when you're using all the objects. Is there some way that I can change that to take into account this situation where when I don't use all the objects? And as luck would have it, yes, there is a way. This is called the permutation formula. This is the notation for the permutation formula. So if you're using a calculator, like the 2 of you that I helped, and I'm sure everyone else, you're going to find a button that will do this calculation for you. It's going to have a P, and it's going to have an N as a subscript on the front, and it's going to have an R on the subscript on the other side. And what this is N stands for the number of objects, And the R stands for how many I'm using, how many I'm selecting. So we're figuring out the number of permutations, that's what this P stands for, the number of permutations of n objects when I select them in groups of R. And here's how you do that. The numerator is going to still be n factorial. Okay, so what n factorial is, that is the permutations of all the objects. Okay, we just saw that on the previous page. If I want to hang all 6 pictures on the wall, then it's n factorial. If I want to put all 7 books on the shelf, that is 7 factorial. If I want to use all 5 letters, that's 5 factorial. That is what we've already done. But now, if I'm not using all the objects, here's what I'm going to do. I need to get rid of the objects I'm not using. So we're going to divide by this. I'm going to take n minus r factorial. So that is the total number of objects minus how many I'm using. That's the leftover objects. So, bless you. What this is this is the permutations of the leftover objects, the ones I'm not using. Just trying to give you this information in a way that it's reasonable to digest, because I know this is probably one of the more difficult things of this chapter. So I'm going to help you with example 8. And I'm going to show you what I expect when you do the test. So example 8 says this: you are among 9 people forming an astronomy club. Astronomy's fun. As a group, you decide to put each person's name in a hat and randomly select a president, a vice president, and a secretary, because there's no better way to pick leadership than randomly. How many different arrangements of objects are possible? Now, before we do the problem, here's what I want you to answer. What about this problem tells me that order is important? Why does order matter? Yeah, there's a hierarchy, right? If you get picked first, you get a different role than if you get picked third, right? So that's why order matters. So when you're doing your homework in this section, that's the thing I want you to ask yourself and get to know, because then when we come back on Tuesday, the opposite question is what you're going to ask is, why doesn't order matter in this problem? Okay, so this order matters because there's a hierarchy. First is president, second is vice president, third is the secretary. All right, so order matters. So here we go. What we're going to do, what we're being asked to do is we're asked to find the number of permutations. How many total objects? 9. I know they're people, but I'm just calling them objects because we're doing math. Okay, I have 9 objects. How many am I choosing? I'm choosing 3. And here's my expectation on the test. Okay, so I'm going to give you a problem almost exactly like this on the test, probably 2. So the first thing you're going to do is you're going to write down this for me. The second thing you're going to write down is this next part. You're going to say, okay, the permutation formula is this. First, it's 9 factorial. That's the number of permutations if I was selecting all 9 people. Then I'm dividing by, well, if I'm selecting 3 people, how many people am I not using? 6, which is 9 minus 3. These are the people, 9 minus 3. Those are the people I'm not using. And at this point, you have an option. If you have a calculator that does permutations, which I'm looking around at the calculators you have, I'm pretty sure everybody has a calculator that does this. So if you don't know where the permutation thing is, or you don't know how to do this, when we do the next problem, just wave your hand in the air and I will help you do that. Okay, so if you have a calculator that does it, then you're going to use it. I'll show you how to do it on mine. If you don't have a calculator that does it, here's what you're going to do. Okay, so if you just have a 4-function calculator, you don't want to spend the $1.25 at the Dollar Tree to get a scientific calculator, or you don't want to borrow one of mine, here's what you're going to do. Okay, the top is 9 factorial. The bottom is 6 factorial. So this is the shortest way I can show you to do this calculation. 9 factorial is 9 times 8 times 7 times 6, 5, 4, 3, 2, 1. 6, 5, 4, 3, 2, 1 is just 6 factorial. The reason I stopped there is because I have a 6 factorial in the denominator. I can just now cancel those, okay, because they're the exact same thing. So I can cancel the 6 factorials, and so the answer is 9 times 8 times 7. But if you have a calculator like this one, most of the calculators function in this way, I'm pretty sure, so don't hold me to it. My permutation button is right above the number 9, so here's what I'm gonna do. First thing you usually have to tell the calculator, and I'm hoping it's true on this one, is you gotta tell the calculator how many objects you have. So I'm gonna hit the number 9. Then I'm going to hit the permutation, and now the calculator is waiting. It says, okay, you've told me it's the permutations of 9 objects. I need to know how many you're using, so I'm gonna hit the number 3, and then equals, and I get 504. So verify that you can get 504 on your calculator. If you can't, then that is a great question, and I will come around individually. And so what I would like you to do is example 9. Do the same thing. I'd also like you to ask yourself the question, why does order matter in this example? Okay, so example 9 says a skiing event has 16 participants. The 5 participants with the fastest times will be listed on the leaderboard. How many different ways are there for the 5 names to be listed? Now, why does order matter on this one? Yeah, it's a leaderboard, right? It's first, second, third, fourth, fifth. So order matters. Okay, so fantastic, great. So I underlined leaderboard because that's why I know it's a permutation problem. Once you identify that, the rest of this shouldn't be too big of a deal once you get used to using this formula. So I have the permutation of 16 objects. I'm choosing 5 of them to put on the leaderboard. I'm going to use the formula, so that is 16 factorial divided by, and you can either write 16 minus 5 factorial, or you can put 11. That's the number of objects I'm not using. At that point, if anyone needs to know how to do this, the longhand method, that's fine, but I'm just going to go to my calculator now, and my calculator says, okay, I've got 16. I'm going to hit my permutation, which is the number 9, and then I'm choosing 5 of them, and we get 524,160. Do you have agreement on that? Is that what you guys got? Okay, if you can't get that, let me know when we're doing the next problem, and we'll run through your calculator again. Okay, we just got a couple more, we got one more of these and then one alteration to make. So example 10, same thing. Okay, so this one says a bicycle club has 10 different routes its members would like to ride. There are 6 dates to fill for trips. How many ways can the different routes be assigned to the available dates? So why does order matter on this problem? It's not necessarily the different roads, it's the fact that there are different dates. Yes, so depending on when the date is picked, that so you can do whatever road on March 1st and March 2nd. So that's how come order is going to matter on this problem. So once you determine this is a permutation problem, I have 10 objects. I've got 10 routes. That looks like a 6. Let me do it a little better. I've got 10 objects. I'm picking 6 of them. So that's 10 factorial over 10 minus 6, or you could write 4 factorial here. I'm just alternating so that we don't get into a rut. So remember, the numerator is the permutations of all the objects. The denominator is the permutations of the objects that I'm not using. And then at this point, I'm going to go to my calculator and I'm going to say, okay, here we go. I've got 10 objects, permutations. I'm using 6 of them, and that is 151,200 different permutations. Okay, so where we've been is we used the counting principle. We came up with this idea of the permutation. It's the ordered arrangement of objects. Then we said, okay, what happens if I don't want to use all the objects? So then we came up with this permutation formula, which is the ordered arrangement of not all the objects. Then the last thing here is, okay, what happens if I need my ordered arrangement, but let's say I have repeated objects or duplicate. So in this problem right here, what I want to do is I want to know how many different ways can the letters in the word Cincinnati be arranged? And I've spelled Cincinnati wrong, haven't I? I don't either. Hang on. I got to pause this because I've used this for 2 semesters and no one's ever. Okay, it turns out I did spell Cincinnati just fine for anybody watching on the video. Okay, so here's how we do this. So we saw on the previous page, I gave you the letters A, B, C, D, and E and said how many ways can these be arranged? And that was a straight 5 factorial because all the letters were different. This time though, I notice I have a couple letters that are repeated. So when you have repeated objects, here's how you find the number of ordered arrangements. So first off, how many letters are in Cincinnati? There's 10. So we're going to start off with the 10 factorial. Okay. Once again, the 10 factorial, that is the ordered arrangement of all the letters. Then what I'm going to do is, since in this case I have 3 n's, and it doesn't matter, they're all the same letter, it doesn't matter where they go, I'm going to divide out the ordered arrangement of those 3 same letters, all the permutations. So what I'm going to do is I'm going to divide by 3 factorial. Okay, and I'm just going to put under here, that's for the n's. There's 3 n's. They're all the same, so I'm going to divide out all the different permutations. I also have c's, and there's 2 c's as long as my eyes are not deceiving me. So I'm going to divide by 2 factorial. Those are my c's. You don't have to put the letters down under here. I'm doing this for your notes. So when you go back later and you're doing your homework, you can see why I did that. And then we have one other letter repeated. That is the i's. And there's 3 of those. Now this, unless you have a calculator that is specifically attuned to probability and statistics, you probably don't have a calculator that's going to do this. What you can do is calculate 10 factorial and then divide by 3 factorial. But what I'm going to do is I'm just going to show you the kind of the brute force method. So 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4, and then 3 times 2 times 1 is 3 factorial. I'm going to leave this 3 factorial the way it is because it's going to cancel with the other one. And the other 2 factorials I'm going to write out. And you should not have a denominator left when you're done with all the canceling. Okay, so you should always get a whole number answer for this if you've done your arithmetic right. So the first 3 factorial is 3, bless you, times 2 times 1. The 2 factorial is 2 times 1. Now I'm ready to cancel and I'm ready to be done with this problem. So the 3 factorials, they go away. See you later. I'm going to say 2. 2 goes into 4 and leaves 2. I'm also going to say that 3 times 2 here, this 3 times 2 is 6. So this 3 times 2 is going to cancel with the 6 in the top. So 3 times 2 is 6 is going to cancel with that 6. So what I'm left with is 10 times 9 times 8 times 7 times 5 times that 2. And that's going to look like 10 times 9 times 8 times 7 times 5 times 2. That's going to be 50,400. Like I said, if you are very confident with your calculator ability, here's what you could do. Okay, instead of doing that, you can say, okay, I've got 10 factorial, so I'm going to do 10 factorial. Then I'm going to divide by 3 factorial. Then I'm going to divide by 2 factorial, which is just 2. Then I'm going to divide by another 3 factorial. And I get 50,400. So if you're confident with your calculator ability, or some of you have the calculator with the display that you can input everything and then just hit enter at the very end, then you can go ahead and input it like that. Okay, but just in case you're like me, I'm not always confident in my calculator ability, I would probably do it like that. All right, so last problem for the day, example 12. How many ways can the letters in the word Mississippi be arranged? All right, well, how many letters do I have in all total? I have 11. So if all the letters were different, I'd be done with the problem and I'd go to my calculator and boom, we'd have an answer. But all these letters are not different, so now I have to divide out the ones that are the same. So I have 4 S's, so I'm going to divide by 4 factorial. That's for my S's. I have what other letters repeat here? I got 4 I's, okay, so 4 factorial for the I's, and then there's 2 P's. Does anything else repeat? Doesn't look like it to me either. And so again, however you choose to do this calculation, whether you're using your calculator or you're using the brute force method like me, so in the top 11 factorial is 11 times 10, 9, 8, 7, 6, 5. And then the 4, 3, 2, 1, I'm going to keep written as 4 factorial because they're going to cancel with this 4 factorial right here. Then the next 4 factorial I wrote as 4, 3, 2, 1. And then the 2 factorial is 2 times 1. And now I'm just going to cancel out what I have in common. So I'm going to say, okay, 2 goes into 6 and leaves 3. This 2 goes into 8 and leaves 4. I can divide this 3 either into the 9 or I can divide this 3 into the 3 that's left there, which I'm going to do. And then this 4, I'm going to divide with the 4 that's already there. And so what I'm left with now is 11 times 10 times 9 times 7 times 5. And I end up with 34,650 different ways to arrange those letters. Does anybody have any questions?